Optimization is a never-ending task that engineers have to perform. However, in today's world, even relatively simple engineering products like pumps have multiple parameters, with design decisions that often fight each other. This makes optimization quite hard, and it also means that multiple parameters have to change at once in order for there to be a meaningful improvement. Let me introduce Tomasz Kotnik, who will show us how to do this.
Hello, my name is Tomáš and I would like to show you how to perform a data analysis using our software. The 3D model you see on the screen was created using Onshape, a cloud-based CAD software. The result will be computed using SimScale, another cloud-based platform for CFD and finite element computations. SimScale allows direct import of a geometry from Onshape. Currently, I have a table with 50 different combinations of input parameters along with their corresponding results obtained from SimScale computations. These data have been loaded into our UptimAI input preprocessor, where I can inspect and visualize them to ensure their correctness. For instance, I can generate scatter plots to examine the distribution of data across the design space to find obvious outliers in data. I will move on to setting up the solver. The solver is the core component of our software package. It's responsible for building a mathematical model, also known as a digital twin. I have selected a predefined input set and configured the solver for both output variables. The second output variable represents efficiency, which is my primary focus. After saving the setup, I will close this module and proceed to running the solver itself. The solver can be launched with a separate graphical user interface, which looks like this. Here I will make sure I'm using the right solver setup and initiate the data analysis. The solver will run for a few moments now, and after that the mathematical model will be ready. Now I will proceed to the post-process of the digital twin. The first feature I will use is the sensitivity analysis, which identifies the most influential input parameters. According to this analysis, the most significant parameters are blade count, blade thickness, and blade angle. The analysis indicates that these blade-related parameters play a crucial role in determining pump efficiency. The other parameters, such as blade radius or diffuser and inlet characteristics, influence the mean value more than the variance of results. Another useful feature is the increment function, which helps determine whether an input parameter affects the output on its own or through interactions with other parameters. For instance, when analyzing the impact of blade count on efficiency, this specific plot suggests that the highest efficiency is achieved with approximately 12 blades. However, parameter interactions must be considered also. For example, the relationship between blade count and blade thickness reveals that at lower blade counts, the blade thickness has very little impact. However, as the blade count increases up to 30, the influence of blade thickness grows significantly, leading to a steep decline in efficiency. I can also show the histogram of results and compare its shape while including or excluding specific input parameters. For example, removing blade thickness from the analysis leads to a significant reduction in variance of efficiency. This indicates that a proper blade thickness can help to avoid inefficient designs. Here, analyzing the blade count confirms its strong influence on both the variance and the mean value of efficiency. That confirms also the findings we found previously in sensitivity analysis and increment functions. I can directly address the best result found in the histogram and what are the corresponding values of input parameters. This is quite easy way how to set up an optimization, and the optimum will be robust. So it is time to use all the information we learned from our mathematical model to use it on our design. The last step is to change the pump geometry according to the results of our analysis. By implementing these optimized parameters, we achieve an improved design, and here it is, our optimal pump configuration. This geometry is used to compute the efficiency of the optimal design in SynScale to prove that our predictions are correct. The optimal efficiency predicted from the UptimAI model is 62.5%, while the computed efficiency is 61.3%. This demonstrates the very good accuracy of the model in the area of interest and the well-predicted optimum.
Thanks, Tomasz. It's hard to see the differences visually, but this emphasizes that optimization can be very subtle, and even minor tweaks can raise good designs into great designs. Let us help you make some great designs with the power of industrial AI.